Welcome to the start of a new unit. Today we're going to be looking at something that I can almost guarantee that most of you have never done before. So just brace yourselves. This is probably something brand new. But in the end, I'm hoping that I can clear up exactly what's going on with this. And when we finish this unit, we're going to be looking at one of my personal favorite areas, which is cryptography. Because talking about modular arithmetic, it's going to lead us into looking at codes, especially in World War II, and how the Allied forces were able to defeat Germany and Japan, and with being able to break their codes when they were communicating. And it really comes down to a lot of modular arithmetic and prime numbers. Okay, so previously, in the last video, I mentioned that Carl Friedrich Gauss introduced our modern symbol for congruence. So today you're going to get to see that modern symbol and what exactly it means as we talk about modular arithmetic and congruence. Okay, in a nutshell, it's kind of, if I could summarize it in one sentence, when you hear modular arithmetic, think in terms of remainders. Think in terms of dividing and seeing what the leftovers are. This is one area where we're less interested in the answer and more interested in what's remaining or left over after we find the answer. Okay, real life example. So let's jump right into a real life example before we start doing any kind of problems. Let's say today is Wednesday. It's actually not. Today's Saturday while I'm recording this, but whatever. Let's pretend it's Wednesday because it's already on the slide. And we're curious what day of the week it's going to be in 23 days. And I mean, 23 days isn't that far away, so you could sit and count on your fingers, Wednesday, Thursday, Friday, Saturday, Sunday, etc. But there's a much faster way, and you can well amaze your friends and get it a lot faster than they can count on their fingers. And that is with using modular arithmetic. So you think about the fact that a week is 7 days long. So 7 was what we're going to divide by. Because we know that every 7 days we're going to be back to a Wednesday, because that's a pretty consistent thing in our calendar. Every 7 days is a week, so 7 days from Wednesday you're going to be at Wednesday again. And every multiple of 7 days you're going to be at Wednesday again. So 7 times 2 and 14 days. 7 times 3, 21 days. 7 times 4, 28 days. So you know how far you'll be every 7 days. And to figure out where you'll be at 23 days, you just need to figure out how far beyond a multiple of 7 you're going to be. Which I mentioned the multiples a minute ago. 7 times 1 is 7. 7 times 2 is 14. 7 times 3 is 21. All right, we're close to 23 without going past it. So let's see. So 21. And if you think about 23, we need to go 2 days past 21. Or if you did a division, 23 divided by 7 days in a week, you would see that your remainder is 2. So you need to go 2 days past Wednesday. So that you can count on your fingers if you want, but you can probably do it in your head too. So Thursday, Friday. Friday is 2 days past Wednesday. So that's what day of the week it'll be in 23 days. All right. What if today is Thursday? And we want to know what day of the week it'll be in 61 days. Now that we've looked at a problem like this, we know exactly how to tackle it. We can say 61 divided by 7. 7 times 8 is 56. So we know in 8 weeks from now, it'll be Thursday still, but it won't quite be 61 days yet. Let's see how far past that we go. Subtract. The remainder is 5. So we're interested in the remainder of 5. Well, today's Thursday. What day is it going to be 5 days past that? So I'm just going to start counting on my fingers. Friday, Saturday, Sunday, Monday, Tuesday. So 5 days past that will be Tuesday. We're looking at 8 weeks, 5 days. When we talk about 61 days. And then it'll be Tuesday again. All right, again, today's Thursday. What day will it be in 3 years and 34 days? It's kind of a fun experiment. You can kind of work backwards and figure out what day you were born, too, without trying to pull up a calendar. It's kind of a fun way to do it. All right, because you know there's 52 weeks in a year. You gotta think about leap years a little bit, but hey, 52 weeks plus 1 day in the leap years, but still, you can figure it out. Same kind of principle, just go in the other direction rather than forward from the day of the week, go backwards from the current day of the week. Okay, so I'm not gonna do that right now, but let's say 3 years, 34 days. We're gonna assume 365 days in a year. For now, we're gonna just skip leap years just to make this simpler. If you were dealing with a leap year, you'd have to add that extra day in there. Because remember, leap year is 366 days. But we're just going to assume there's no leap year. Making life easy on us for now. So that's 1,095 days. Yes, I'll write up here, assume no leap year. Plus we had those 34 days. So we're trying to see how many total days we're talking about here. Okay, we're talking about 1,129 days. So let's divide 1,129 by 7. So we're looking at 161 weeks plus 2 days left over. So we just got to look at 2 days past Thursday. You can just count on your fingers. You're looking at that too. If it's already Thursday, 2 days later, it'll be Saturday. And there you have it. So that's a real world type example of what's going on, with modular arithmetic and looking at those remainders. But we're going to get all mathy, of course. And we're going to officially talk about something called congruence. That's an essential part of modular arithmetic. And this is where Carl Friedrich Gauss came in. That little symbol right there with the, looks like a 3-barred equal sign, that's our symbol for congruence. So if you see that, in this case you've got A is congruent to B, and in parentheses you see mod M, also known as modulus M. So this is read, A is congruent to B modulo M. You might also hear modulus M. And it means that A and B basically have the same remainder when divided by M. And then some basics of division, like if you go way back to 3rd and 4th grade when you were first really learning about division, if A and B both have the same remainder when divided by M, that means that M will go evenly into their difference too. So we'll look at that as well in a few minutes. All right. So an example, well, you know what? Let me go back up here for just a second. And in this slide, so an example of something that would be true, you could say that 17 is congruent to 22 mod 5. That's an example. Because if you divide 17 by 5, you get a remainder of 2. And if you do 22 divided by 5, you also get a remainder of 2. So that remainder of 2 is what's important here. They both have the same remainder. And that's what makes them congruent. All right, so with that in mind, like if they give you a problem and they don't fill in the blank, like let's say they say 38 is congruent to what? Mod 9. You can say, oh, okay, we've got that mod there. The modulus, the 9, is what you're dividing by. That's your divisor. So what we could do to find an answer to that is we could say 38 divided by 9 and see what the remainder is. Whatever the remainder is goes there because that's going to, if you divide the remainder by 9, you'll have the same remainder too. So you can just divide and see. So 9 times 4 is 36, and you get a 2. So you can very correctly say that 38 is congruent to 2 mod 9. I know that sounds weird, but if you divide 2 by 9, you also get a remainder of 2. So that's, the remainder would be its own, would be the remainder if you divide by 9. So that's a perfectly legal example. And normally with these kinds of problems where they want you to fill in the blanks, you're trying to find the smallest positive number that'll work there. Some number less, some non-negative number, or I should say non-negative, not positive, because 0 can go there too. So some non-negative number less than your modulus. So usually if there's a blank, they're wanting you to find a number from, like, if your modulus is 9, they want you to find a number from 0 to 8 that works there. But that's not the only kind of number that works. You could say that 38 is congruent to 11 mod 9. That works. As soon as you divide 11 by 9, 9 goes in one time, but you have that remainder of 2. You could say that 38 is congruent to 20 mod 9. That works. Because 20 divided by 9, 9 goes in 2 times, remainder of 2. You could say 38 is congruent to 29 mod 9. As soon as you divide 29 by 9, you get 3, remainder 2. So once again, that remainder of 2 is what's important here. All of those are correct answers, and there's actually many, many more answers that would work in that blank. That would be correct. You can even go negative. I'll show you about that in a minute. We haven't done negative yet, but you can. So we'll get to that in a minute. Oops, excuse me. I accidentally pushed something on my computer here. All right, let's do one more fill in the blank. Let's say we have 43 is congruent to what mod 6? Well, if you think you have a handle on it, I encourage you to, at any time, like, pause the video and see if you can jump ahead and work out the example before I do. Since it's a video, you can pause it, try it, and then when you continue the video, you'll see if you got the same thing or not. It's a good way to practice along with us. All right, so quick way to figure out something that works there. You can do 43 divided by the modulus 6. 6 times 7 is 42. So you get a remainder of 1. So 43 is congruent to 1 mod 6. Now's a good time to pause and maybe think, what are some other numbers that would work there? All right, so if you paused it, I'm wondering if you came up with the same ones I did. There's a lot of them. There's all kinds of different correct answers. There's like infinite numbers that'll work, honestly. But my first ones that I think of are 7, 13, 19, there's many, many more. Those all work. Typically, these problems are asking you, though, for that smallest non-negative number. So typically, they're asking you for this one right here, the 1. But all the others are technically correct also. Now, you might be wondering, I did not work all those out in advance, but I sure did spit them out pretty quickly. You might be wondering how I did that. If you start looking at all the numbers that when divided by 6 have a remainder of 1, you're going to find a pattern. And that's true for any of the remainders. Like if you divide by 6 and have a remainder of 2, or if you divide by 6 and have a remainder of 3, you're going to see a pattern. You're going to notice that all of these results here differ by 6 or some multiple of 6. Like if you do 7 minus 1, that's 6. If you do 13 minus 7, that's 6. If you do 19 minus 13, That's 6. If you do 13 minus 1, that's 12, which is 6 times 2, the multiple of 6. If you do 19 minus 7, that's 12, which is also a multiple of 6, 6 times 2. If you do 19 minus 1, that's 18, which is the same thing as 6 times 3. So whenever you're focusing on a certain remainder in relation to your modulus, all of the results that can go in that blank that have the same remainder will differ by some multiple of 6. And you remember earlier, right here, where I said that m divides a minus b? Well, that applies to what's happening now, okay? Your 6 will go evenly into whatever two numbers you put here. Like if you do 43 minus 1, you get 42. 6 goes evenly into 42. 6 times 7 is 42. That's what this little symbol here means. It means it divides evenly into that number. 6 divides evenly into 42. 6 times 7 with a remainder of 0. If you subtract 43 minus 7, same idea. You get 36. 6 goes evenly into 36. If you subtract 43 minus 13, 6 goes evenly into 30. If you subtract 43 minus 19, 6 goes evenly into 24. So that's kind of a quick way, too, to check to make sure you have answers at work. You should be able to subtract the A and B, and then 6 should be able to go evenly into that. If you subtract and get a negative and you're like, oh, I'm not sure about that, just switch the order of subtraction. It's all right. If you did 1 minus 43 and you're like, I don't know about negative 42, switch it and do 43 minus 1 and see what you get. It's fine. But that's another little rule with the modular arithmetic. Which leads us into modulo classes. In a modulo system, numbers with the same remainder after being divided by the modulus all belong to the same modulo class. Numbers in the same modulo class differ by multiple of the modulo. And then the remainders, or the solutions, will range from 0 up to 1 below the modulus. Like if you divide by number, your remainder can never equal or exceed your divisor. If it does, then you did something wrong. So that's the same thing here. These remainders, like if you're mod 3, your remainders can only be 0, 1, or 2. If you're mod 5, the remainders can only be 0, 1, 2, 3, or 4. If you're mod 8, your remainders can be 0, 1, 2, 3, 4, 5, 6, 7. That's it. All right, I wanted to do an example of what's going on with, like, let's say modulo 3 classes. That's where I wanted to go with this. Just do, like, if in your book they do a modulo 7 classes chart on page 540. And then I think there was another chart. Well, page 540 for sure. Yeah. So page 540 has modulo 7 in the current book. If you're watching this in the future, you might have a different page number or a different book. But for now, page 540 shows mod 7. So we're going to keep it shorter, though, and do mod 3. Okay, so if you're dividing by 3, if your modulus is 3, your possible remainders are 0 up through 1 less than the modulus of 3. And when we talk remainders, we're talking nice whole numbers. So your possible remainders are 0, 1, or 2. So I'm interested in making a chart with some of the numbers that would have those remainders. Not going to do all of them. And how about we start with 0? But I'm going to do something else. So before you get gung-ho, let's put 0 here. 0 divided by 3, or 3 into 0, goes in 0 times remainder 0. So 0 has a remainder of 0 when you divide by 3. 1 has a remainder of 1 when you divide by 3. 2 has a remainder of 2 when you divide by 3. Now if you divide 3 by 3, that's also a remainder of 0. So 3 gets to go here in this column. How about we try to do this to make sure we know that these are columns. These are the possible remainders up here. I'm trying to just divide it out here so we can see what we're doing. Maybe I'll get a little fancier and even use like a highlighter. Let's highlight the remainders in blue. So those are the possible remainders. All right. If you divide 4 by 3, you get a remainder of 1. So that gets to go in this column. If you divide 5 by 3, you get a remainder of 2. So that goes in this column. And so on. If you divide 6 by 3, you get a remainder of 0. If you divide 7 by 3, you get a remainder of 1. If you divide 8 by 3, you get a remainder of 2. And so forth. Now, if you start looking at these columns, and you start to see kind of a pattern, like your remainders were 0, 1, 2 in one row. So you had a row here with 0, 1, 2. And then when you got to 3, it started a new row, 3, 4, 5. Then you got to 6, it started a new row, 6, 7, 8. You can count backwards to fill in this chart with negatives also. Like if 0's here, you can count backwards and do -1, -2, -3, -4, -5, -6, and so on. So this can include both positives and negatives. Now notice another thing, when you start looking at your columns, you can pick any two numbers in a column and they are going to be, the result's going to be some multiple of 3, your modulus. So like 6 minus 3 is 3, 8 minus 5 is 3. But you can also do like 6 minus 0 is 6. That's a multiple of 3. Or you could do 7 minus 1 is 6. That's a multiple of 3. But that even works with your negative numbers. Like if you did 6 minus -3, you get 9, right? Well, 9 is 3 times 3. That is still a multiple of 3. So 3 divides evenly into 6 minus -3. Any two numbers in the same column will have the same remainder when divided by 3. Also, any two numbers in the same column, you can subtract them, and 3 will go evenly into that result, into that difference. If you did 5 minus -4, you'll get 9, which we know is 3 times 3. If you did 8 minus -4, those are two in the same column, you get 12. 3 times 4 is 12. 3 divides evenly into 12. So this chart might be helpful too when you start ending up with having to work with negative numbers. All right, so let's say you have an example. I'm pulling these out of the book, but let's say you have -27 and you're trying to figure out what that's congruent to mod 8. You might be like, well, if I divide by 8, I have no idea how to figure out the remainder because that's a -27. But you know that if you're talking with modulo 8 classes, every number in the same column, the numbers in the same column will differ by a multiple of your modulus, in this case 8. And also every number in the same column has the same remainder when divided by 8. So you can take -27 and you can start adding 8 to it, your modulus. So you do that, you get what, -19. So technically -27 is congruent to -19 mod 8. But then you can take -19 and add 8 to that, and you get -11. So you could also say -27 is congruent to -11 mod 8. You can take -11, add 8 to that, and you get -3. So -27 is congruent to -3 mod 8. If you add -3 and 8 together, you get 5. -27 is congruent to 5 mod 8. Take 5 and 8, you get 13. -27 is congruent to 13 mod 8. Typically, they're looking, though, for this answer right here. They're looking for the smallest non-negative number. So typically they're looking for the 5 if you're being asked for this problem, even though there's multiple correct answers. And if you look at this, 8 divides evenly into 5 minus negative 27, because 5 minus negative 27 is 32. 8 times 4 is 32. So those two numbers, like if you subtract them, the difference, 8 divides evenly into the difference. That's a quick way to check too. Make sure you didn't accidentally mess up something along the way. And I went step by step and just kept adding 8. But from the beginning, if I had thought about 8's multiples, I could have said, you know what? 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24, 8 times 4 is 32. 32 would be the first multiple, positive multiple, that would add and give us something positive. So then I could have found the answer that way. Instead of just keep adding 8 over and over again, I could have just thought about multiples of 8 and added the first appropriate multiple to give me that positive answer. But that's basically what's going on with the negatives. Negative 39 is congruent to what mod 7? So modulus is 7, so we're thinking about multiples of 7. So you think about 7. You got 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21, 7 times 4 is 28, 7 times 5 is 35, 7 times 6 is 42. All right, 42 is the first thing that when you add it to negative 39, you're going to get that positive. So you get a 3. So negative 39 is congruent to 3 mod 7. And again, there's multiple correct answers, but typically they're looking for something, the first non-negative number that you can put in that blank. All right, one last topic just in this introduction to congruence. Modular arithmetic systems under the operation of addition are something called commutative groups. This is not something I'm going to focus on too much in this unit, but it is mentioned in the book and there are some homework problems on it. And this is something that if you are a math major and you take something called abstract algebra, you would start dealing with this more. When I was in college at Florida Southern, they called it modern algebra, but still. Believe it or not, algebra goes way above and beyond what you do in high school. Algebra 1 is just the very tip of the big picture. But anyways, a group is a mathematical system. So it has a set of elements and at least one binary operation. So operation where you can do it between two things. In this case, we're going to be dealing with addition. And it has to meet the following requirements. It has to be something called closed. It has to have an identity element. It has to have an inverse. It has to be associative. And we're going to deal with a commutative group. They also call that abelian, named for Abel, a mathematician. And that satisfies the commutative property also. So commutative property, remember, the order doesn't matter. Like in general with addition, 2 plus 3 gives you the same result as 3 plus 2. In multiplication, you have the commutative property as well. 3 times 8 gives you the same thing as 8 times 3. And that's true with these groups. If you can add one direction and also add the other direction and get the same answer, then the group is considered to be commutative. All right, so your book deals with this, a mod 5 addition table on page 544. I think we're just going to do a mod 3 or something to keep it kind of short. Or maybe, yeah, because your book doesn't do a mod 3, so just kind of keep it short for the purpose of the notes. But if you wanted to look more deeply at this, another example, page 544 has a mod 5 version. But we are, in this table, we're looking for the following commutative group properties. Looking for something called closure, looking for something called the identity element, looking for the inverse element, looking to see if the associative property is satisfied, and looking to see if the commutative property is satisfied. If those 5 things are working, then we definitely have a group and it's commutative. The first 4 define the group. The 5th one defines a abelian group, commutative. Okay, so we're going to make a little table. And we're going to do a mod 3 addition table. Okay, so if we're dealing with mod 3, our remainders can only be 0, 1, or 2. And we're looking at addition, so we're going to put a plus sign right there. The remainder is going to be 0, 1, or 2. I think I'll go and erase this tiny bit over here. Ah, it erases the whole thing. All right, so make that a little darker. Dealing with addition. So we gotta take these and add, and then figure out what the remainder is when we add them together in mod 3. So like, let's take 0 and 0. So like if you did 0 plus 0, you get 0. And 0 is congruent to 0 mod 3. So we put a 0 here. Then if we do 0 plus 1, that's 1. And 1 is congruent to 1 mod 3. So we put a 1 here. If we did 0 plus 2, that's 2. And 2 is congruent to 2 mod 3. So put a 2 here. Okay, next row, we got 1 plus 0. It's also 1. We already know that that's congruent to 1 mod 3. 1 plus 1 is 2. We already know that's congruent to 2 mod 3. 1 plus 2 is 3. 3 is congruent to 0 mod 3. Because you divide 3 by itself, you get a remainder of 0. Starting to run out of space. Let me slide this up a little bit. If we do next row, 2 plus 0, we get 2. That's congruent to 2 mod 3. If we do 2 plus 1, that's 3. 3 is congruent to 0 mod 3. We already know that from earlier. And if we do 2 plus 2, that's 4. And then 4 is congruent to 1 mod 3. Because if you divide 4 by 3, you get a remainder of 1. All right, so there's our table, our mod 3 addition table. So now you know in modular arithmetic with modulus 3, if you add 0 plus 0, you actually get 0. If you add 2 plus 2, you actually get 1. Because the whole modular thing. I know real life, like normally you would say 2 plus 2 is 4, but we're talking mod 3, so it would be the remainder 1. Okay, so there's the addition table. Let's verify that this is a group. So abelian or commutative group. Okay, so first we have to deal with closure. Is every entry in the table a member of the set? A member of the set 0, 1, or 2. It can only be 0, 1, or 2 because we're talking modular 3 arithmetic. You know, you can only have answers 0, 1, or 2. And the answer is yes. So this is closed. Your elements all are, match up with modular 3. Identity element. Is there an element that when you add, you get back the same number? Is there an element that when added results in the original number? every time. So we go back up to our table. And it looks like, to me, it looks like 0 is our prime candidate. Because you start looking at what's happening there with 0. Try to pick a color that makes sense to me. I'll just use gray. You add 0 plus, like, let's say you're focusing in on 0 here. You add 0 and 0. You add this 0 to that 0, you get 0. You add 1 to that 0, you get 1. You add 2 to that 0, you get 2. But at the same time, like if you're looking at the 0 up top, so let's do this. Let's make that gray, and let's make that yellow, so that way you can see the matching. So if you're adding the 0 up top, this 0 plus that 0 is 0. That 1 plus that 0 is 1. That 2 plus that 0 is 2. So either way, when you add 0 to a row or you add 0 on a column, you end up getting back the original numbers. So in this case, yes, there's, there we go. So yes, there is an identity element. It is 0. Number 3, inverse element. When you look at the table, does every element have an inverse? In other words, is there something that adds and gets back the identity element of 0? So go back up to our chart. Well, in this case, 0 is its own inverse, because 0 plus 0 is 0. So we got that. So for 0, we got 0 plus 0 equals 0. But we got to figure out, is there something we can add to 1 to get 0? To 2 to get 0? Let's see here. If we add 1 plus 2, we get 0. So yeah, adding 1 plus 2 gets 0. And what about 2? If we add 2 plus 1, we get 0. So yeah, each element has an inverse. Each element has a number that you can add to it and get back the identity element. So, yep, every element has an inverse. So that's number 3. Number 4, associative property. That's the one with the parentheses. Can we take 0 plus 1 plus 2 and get the same answer as 0 plus 1 plus 2? All right, going up to our chart, 1 plus 2. If I add 1 and 2 together, I get 0. So I get 0 plus 0, and I already know that 0 plus 0 is 0. And then back to our chart, if I add 0 and 1 together, I get 1. And then if I add 1 plus 2 together, I get 0. So yeah, the associative property holds. To take 3 numbers and add them up, it doesn't matter where you put the parentheses, you're going to ultimately end up with the same answer for both of them. That's what the associative property says. And you can test this a few more times with other numbers and other orders, and you'll still find that it works. And then finally, the commutative property. can you do a plus b and equal b plus a for all elements? Well, start taking a look at it. Like, let's say you do 1 plus 2. Can you do 2 plus 1 and get the same answer? If you do 1 plus 2, does that equal 2 plus 1? Let me look back up here. 1 plus 2 is 0. 2 plus 1 is also 0. And you could test that for every element, A, B. How about 1 plus 3? Does that equal 3 plus 1? Not 3. Sorry. We're only doing 0, 1, and 2. Getting carried away. Let me erase that. Let's do 1 plus 0, 0 plus 1. So 0 and 1, 1 and 2, 0 and 2. Can we do 2 plus 0 and get the same thing as 0 plus 2? All right, let's do 1 and 0, 0 and 1. 1 plus 0 is 1. 0 plus 1 is also 1. So yes, that comes out to 1 and 1. So 1 equals 1. Yes. And then 2 plus 0 is 2. 0 plus 2 is also 2. So yes, that works out as well. So yeah. So this is an abelian group. It fits all 5 of these requirements. First 4 are the requirements for being a group. 5th one's for being a commutative or abelian group. So there you go. So I'm going to talk about that a little bit. Again, don't stress too much over it. Just get through the homework because it's not going to be a huge part of your assessment in the class, but it's in there. If you understand this, then you'll even have a much deeper understanding of modular arithmetic. All right, so I'm going to cut this video here. Next time we come back, we're going to get into doing some more operations like addition and subtraction and multiplication and all that, dealing with congruence. And then I'll probably have a 3rd video where I really get into using congruence and all that for the cryptography, the secret codes. I promised before that we would talk a little bit more in depth about that. So that part I'm getting excited about. But thank you for joining us, and I will see you again soon for more on modular arithmetic in the congruence.